finishing up a couple more examples. So let's do let's do 2.22. All right, so in this problem, it says the steady state temperature distribution in a one-dimensional wall of thermal conductivity 50 watts per meters Kelvin and thickness 50 millimeters is observed to be temperature in degrees Celsius equal to A plus BX squared, where A is 200 degrees Celsius, B is negative 2,000 degrees Celsius per meter squared, and X is in meters. Part A is what is the generation rate, Q dot, in the wall, and B is determine the heat fluxes at the two wall faces. In what manner are these heat fluxes related to the heat generation rate? Okay. So we have steady state, it's a one-dimensional wall. They give us the thermal conductivity, K, which is 50 watts per meters Kelvin. They give us a temperature distribution. So we have A plus BX squared, where A is equal to 200 C and B is equal to negative 2,000 C per meters squared, right? They want us to find, and X is in meters. Okay. They want us to find the heat generation rate, Q dot, in the wall. Generation rate, so that's Q dot. And then part B is determine the heat fluxes at the two wall faces. So heat fluxes, and then at the two walls. So that would be at X equals 0, the heat flux, at X equals L, heat flux. And then they want to know what manner are these heat fluxes related to the heat generation rate. So how are they related? Q dot. All right, let's create a schematic for this one. So if we do our plane wall, and we have X in that direction, and that's a length of L, okay? And then if we were to just plot, we're given this temperature distribution with the constant, so if we were to just plot what that would look like, it's going to look like this. Okay, so let's assumptions first. Where do we start for part A, we need to find the heat generation rate. So where do we begin to get that?
Start off with the COE.
COE? Okay, we can go that route. There's actually two ways to do this. Okay, so if we go with the COE, all right, what do we have here? Can we cancel anything?
We have steady state, so dE storage over dt is 0.
We have steady state, so what? Sorry.
So that's 0. That's it.
Yeah, 0. Okay. All right, so we have, do we have energy in and energy out?
We have flux in and flux out essentially with the temperature distribution. So we can say heat flux times the area using dt over dx.
Yep.
Or
so
because it's because it's in 1D, we could also, I see what you mean by the second method then. So
right. We'll do that next. We'll wait a second on that. All right, so which way is the heat transfer going? Is it going from left to right or right to left? Through this wall.
Left to right?
Yeah. So we have heat flux going that way. So that means, energy out of the wall would be over here. Any energy in would be on the left. And then energy generated. Okay, what's the units of Q dot? Does anyone remember?
Watts.
Q dot is, so EG dot is watts. Q dot, the lowercase q that we're looking for, is per unit of volume. Okay, so we got to multiply times volume to get energy. Okay. Oh, I ended up doing that in red, all that line, but we'll leave it be. All right, so we have this so far. So how can we simplify this?
Areas are not changing, so we can cancel those out and the volume becomes just L.
Yes, since this is area times L, area cancels. So then if we rearranged, you have this. Okay, so we have L that was given to us, right? Did I write it down? No, I missed it. Sorry. It was given to us, though. L is 0.05 meters. Okay. All right, so how do we get these heat fluxes then? X equals 0 and X equals L.
We could use Fourier's law, right?
Yep, so if we use Fourier's law for heat flux, and the X direction looks like this, right? So how do we get dt dx?
Differentiate whatever or integrate whatever is given to us.
Differentiate. Yep. So we have our we have t equals a plus bx squared, right? So we take the derivative, and then put that times that k, right? So we have 2bx. So that gives us the heat flux as a function of x. So at any location x, we could get the heat flux, right? Well, we want it at 0 and L, right? So if we are looking for 0, what do we get for our heat flux?
0.
Yeah, so we have 0 watts per meter squared. And at L, plug in L, we get negative 2 kBl, which if we substitute in, we will get 10,000 watts per meter squared, right? Because we were given K, we have the constant B, we were given L. Right? So then we have, back up here, we have this, we have L. We can just solve for our heat generation rate, okay, and for volumetric heat generation rate. So we get then 2 times 10 to the 5th watts per meters cubed. Okay, so that got us 2 times 10 to the 5th watts per meters cubed, which was our volumetric heat generation rate. Any questions so far on this one?
Yeah. How did you decide on the shape of the curve?
Up here?
Yeah.
So it gave us negative 2,000. So that'll be a negative right here in front of our x squared, right? So that would, if you think of your parabolic relationship, right? And we don't have a constant with times x, right? So there's no, so all you have is this plus a at it. So you have that curve, that looks like this, right? So it's,
yeah, that makes sense. I forgot that the b was a negative value because I was looking at it as just a plus bx, and I was like, why is it looked upside down then? But
yeah, yep. And so that tells us the shape there, right? If it was positive, we would have it flip the other way, and that really tells us a lot actually about what the generation rate is, whether it's positive or negative. This actually tells us a lot. That squared term is because there's generation rate. Okay, there wouldn't be a squared term if there wasn't generation. Because we would have, if there wasn't generation rate, you would have heat flux in is equal to, or heat flux in is equal to heat flux out. And this would be 0. And for that to occur, that means the slope has to be the same all the way through, which would mean it would have to be like a line that's just a constant slope like that, which would have no generation rate because the heat flux here and the heat flux there are the same. Any other questions? Yeah, the other thing we saw is 0, right? What's 0 heat flux? What does that tell us? What kind of boundary condition do we have on the left?
insulated.
Yeah, so it's an insulated, right? So that means this is basically like this is insulated. Or its symmetry is the other one, because if this wall had the same thickness the other way and the same thing happening on the left, you would have a curve that's identical the other way with the slope being 0 right there, okay? So they asked us in part B what the heat flux was at the wall surfaces, and we actually had to solve it for at x equals 0 and x equals L for this method of solving it, right? For solving for the volumetric heat generation rate. What's a different way? What's the other way? As I mentioned, there's two ways. So what's the other way to get the to start the process to get the volumetric heat generation rate?
Using the heat equation and using our boundary conditions.
Yeah, so if we did the heat equation, right? So I'm going to take the one already with constant properties assumed. All right, so we have the heat equation that already assumes constant properties. And then we say steady state up here, so let's put that one to it. Steady state, that's that one. What else can I assume on this equation?
1D.
1D.
Yeah, so we have just a plain wall, x direction, so there's no two-dimensional, three-dimensional conduction. So we have basically one dimension, right? So we simplify this, and it ends up just being an ordinary, right? So there's no y, there's no z, there's no t, so we don't have to do the partial anymore. Temperature is just a function of the x direction. Okay, so if we rearrange for what we're the volumetric heat generation rate, we have this. Okay, so we would just need to take what? So
The second derivative of your t.
yeah. So we already took the first derivative right here, right? So we have it right here. So if we take the derivative again, right? So if we say dt dx, we have it. Our first was 2bx. We'll just get 2b, right? And then if we plug in, we'll get the same thing. Which is our 2 times 10 to the 5th watts per meters cubed. And they ask us, in what manner are these heat fluxes related to the heat generation rate? And we really already, by showing this COE version, we kind of showed how they were related, right? How that heat generation rate was related. Okay. By going down the COE method. All right, we looked at it basically as like that, right? So energy in on the left, energy out on the right. We have our energy generated inside our boundary. And that's what we solved.
So for this type of question on an exam, if we just show the COE version of it, would that be sufficient, or would we have to draw that schematic as well?
Or would you have to go the other route? No, if you're solving the problem, you can solve the problem, you know, whichever way. You just got to show your work, whether you did COE or heat equation, both
As in,
valid.
like, for example, like if we went with the second method of using the heat equation and then we came across to a part B, would we have to show that they're related through the conservation of energy? Or
Yeah.
which, okay.
Or in words, talk about it, and that for that one.
Okay. Thank you.
Mm-hmm. Any other questions? All right, so we're going to do one more example problem from 2. We'll do 2.38. Passage of an electric current through a long conducting rod of radius Ri and thermal conductivity Kr, K subscript R, results in uniform volumetric heating at a rate of Q dot. The conducting rod is wrapped in an electrically non-conducting cladding material of outer radius Ro and thermal conductivity K subscript C, and convection cooling is provided by an adjoining fluid. For steady state conditions, write appropriate forms of the heat equations for the rod and cladding. Express appropriate boundary conditions for the solution of these equations. All right, so we're given a conducting rod, which has thermal conductivity, Kr. It has a outer radius, so radius Ri, and it has a uniform volumetric heating rate of Q dot. And then there's a cladding material around it. That has an outer radius Ro, thermal conductivity K subscript C, and then there's convection cooling. So that gives us H and T infinity. You want us to, and then they give us a schematic, which I'll draw in a minute. They want us to find for steady state heat equation for the rod and the cladding, and then express appropriate boundary conditions for the solution of these equations. So then also boundary conditions. so schematic. All right, so we have then the conducting rod in the center, so that has our I, and then we have the cladding, it's our O. Cladding material also has its conductivity Kc. The conducting material inside has, Q dot. I'm going to actually move this outside. So it's the conducting rod, and that has Q dot and K R's. And then the cladding material is Kc. All right. And then we have some fluid, a convection coefficient, and T infinity. Okay. Any questions? All right, so we have a conducting rod in the center, okay, and then the cladding material outside of that. Okay, the conducting material, they give us K thermal conductivity, the radius of it, volumetric heating, and the cladding material is non-conducting. It has an outer radius and a thermal conductivity, and then we have convection cooling on the outside surface. They want us to get the heat equation for each and the boundary conditions. Okay. So where do we start?
With our heat equation.
Which one? Do I utilize this one?
No, use the cylindrical one.
Yeah, so we have our coordinate system choice would be better with the cylindrical because we have a cylinder here, right? You can use any coordinate system for any geometry, but it doesn't make the problem easy if you're trying to use the Cartesian with the cylindrical here, okay? So that's where it's better to use that, right? So I'll start with the heat equation, which this one's a fun one. Cylindrical. So what can I assume, or what can we assume or cancel in this case?
Well, we have steady state, so whatever's on the right side of the equal sign goes to 0.
Okay.
And we also have convection cooling, so that's another boundary condition.
Well, that'll be a boundary condition. Let's first, what is this? Convection cooling. Steady
Can we
state.
do constant properties then?
So constant properties, yeah. Anything else? To simplify this problem,
1D.
so one-dimensional, right? We're not, if we're looking at this geometry, what's going on here, right? We're not seeing heat transfer occurring, you know, around the angle here, right? It's not a problem that looks like it has heat transfer going around that, so we don't have to worry about that. The other thing is we don't see any heat transfer going in this Z direction here, right? It's all across and looking at the temperatures changing in that radial direction, so we can assume we're more of a 1D problem here, right? And that's a long kind of rod. All right, so that cancels off. This term and this term. And then we said I had constant properties, so that takes this out of the DDR because of now the K is not changing as you go through the material. Okay, so although you see the K changing from the rod to the cladding material, but we'll have a different heat equation to solve for each of those. Okay. All right, so it's K over R. And the only one left is R, right? So we don't have any partial anymore. Temperature is only a function of R in this case. Oop. All right. So we have this, right? So first off, we need a heat equation for the rod, and then we'll talk about the cladding material. For the rod, is this equation correct we see above, or do we need to change it at all? Or so this is the conducting rod through the center. It's the correct one. We'll just leave it. We just got to substitute in RKR. And then we'll also call this P subscript R. Okay, so that's our equation, our heat equation that would be solved for the rod. So for the cladding, do we have to change this heat equation for the cladding?
We just need to add in K sub C and R outer, right?
Well, yeah, when R outer, yeah, that goes with the boundary conditions. Is there anything we
Okay.
cancel in the cladding material?
Q dot, we can get rid of that.
Okay, so if we do that, we got KC over R, DDR. We have this for the cladding because there's no conduction going through the material that generates uniform volumetric heating. The other thing that occurs because of that, now we can, since there's no Q dot, we can get rid of this term, just divide it out, and our equation gets a little simpler. For the cladding. Okay. All right, so now boundary conditions. Are there any questions on above first? All right, boundary conditions. We have two heat equations, right? We have this one, and this one, and they both have an order of 2 in the R direction. So they'll each need 2 boundary conditions. Okay, the rod needs 2 boundary conditions, the cladding material needs 2 boundary conditions. So what boundary conditions do we have?
Convection cooling.
All right, so we have convection on the outside, right? So we'll do that one first. So that's convection, right? And that actually comes from doing a COE on the outer surface. Okay. All right, so that's one. We need 3 more. Yeah, if we applied a COE on that outer surface, right, we would see that boundary condition. All right, so what's our, any other,
Could we say constant heat flux?
where, on which boundary?
For the rod.
At what location though?
Oh, at R is equal to Ri.
Yeah, so right here, we have constant heat flux from the rod to the cladding. Okay, so if we write that down, we have and that's our constant heat flux, which is from the COE at the inner surface. Okay, so you know, if you think about it, you just see energy in equals energy out at that surface right here. And that's heat flux going in and out of that surface. All right, so we need 2 more. Any ideas? These are the trickier ones. So at that interface where they interface together, we have thermal equilibrium, which means the temperature of the rod at Ri is equal to the temperature of the cladding at Ri. So this is constant surface temperature. Or I shouldn't say constant surface temperature. Yeah, it's steady state. So constant temperature, and that comes from thermal equilibrium. All right, so that's that one. Questions on that one? All right, so then there's one more. And this one, so we've talked about the outside surface and then we got 2 at the interface, which really is good because that's where we have 2 materials, right? So we'd have 2 boundary conditions there. We had the conducting and the cladding material meets right there. So we got 2 boundary conditions from that. Okay, so the last one is actually right at the center point here, when R is equal to R0. Any ideas? All right, it's a tricky one, but it's also the given once we understand cylindrical or spherical coordinates. What ends up happening is we have symmetry at that location. So the dt dr at r equals 0 is 0. So that's symmetry. Okay, you see it at table 2.2 for any of these two. So symmetry, what is that in this case? So what we have in this case, if you look at this, everything heat transfer wise would radiate from the center. Okay, so if you're looking, let's draw some diagrams here. If we looked at it this way, or say from the side view, and we did our temperature profile, right? So you have the center, right? If we had center here again, like let's say this is our center point. It's not really good center right there. If we look at it in the radial direction, it's going to have a slope that's 0 at the center because it's everything's surrounding it, right, from all sides. So you're going to end up with this slope at the center point here. And if you look at, you're going to have heat this way, or in, right? But it's always the same because it's always going in from that center point, in or out, right? Because you have this symmetry of this point in the center of your coordinate system. Okay, so you can't have, because you have kind of the same boundary out here, you can't have your temperature profile looking like this or anything like that. You wouldn't have it looking like that, like this, because you have this center point. So it creates this symmetry automatically just because of the geometry. And this occurs in a cylinder, and this occurs in a spherical system. So we automatically have that boundary condition. So that's the nice thing about it. You just got to remember about those coordinate systems that you automatically have that. Any questions? Okay. Hopefully that means you understand it. But that's the 4 boundary conditions, right? So we have, like these 2 for the rod, and you got like these 2 for the cladding. To plug into our constants when we integrate these equations twice.